Okay, friends, we are on page 48. Now, I'm having a little bit of technology issues today because my school computer is not turning on, black screen of death. So I went home and I got my home laptop. So now I'm working on that, but it does weird things when I'm like using OneNote, which is this program that I write in, and it irritates me. So if you see me do this, it's because this is doing something bizarre. It's nothing to do with you guys. Okay? So, dilutions. Key idea. Do we remember how to do dilutions? Yeah? Maybe? Okay. Dilutions basically just involves adding water. Okay? Or you could add a different solution, but mostly just adding water. So if we started with, the key idea here is that the number of moles of solute stays the same. So if we are going to dilute a solution, let's say we have one of these little black dots represents a mole. We have 2 moles in 1 liter. And so that obviously is 2 moles per liter. But now if we add 1 liter of water, nothing has happened to those 2 moles. We still have 2 moles. But now it is in a total volume of 2 liters. So our moles have stayed the same, but our volume has changed. And so now we have 2 moles in 2 liters, which is 1 mole per liter. Yes? Now, one thing you'll notice here is that when we doubled the volume, what happens to the concentration? It halves. What type of relationship is that? That is an inverse relationship. There's an inverse relationship between concentration and volume. That can be a nice little intuitive thing to know, okay? A lot of the time is that as one goes up, the other goes down, and it goes proportionally to the inverse. So in any type of dilution where you are being asked to what is the new concentration, you are going to, number 1, and you see what it does? This is what irritates me. I'm like, why is it doing that? And then I have to tap the page. And then this, can you guys see that little cross thing? Like, what is that? Why is that there? It's trying to grab things and move them. It's very irritating. But anyway, I think I can make it right. So number 1, what we're going to do is we're going to find the moles. So in any dilution problem, if you don't know what else to do, you're going to find the moles. Okay? So 1, find the moles. 2, if you're being asked to find the concentration, if that's what you're asked for, you just take your moles and you divide by the new larger volume. Yes? So for example, if we have 2 liters of a 9 molar solution, now remember, what does of mean? Of means multiplication times, okay? So we have 2 liters of, and remember, what does capital M mean? Molar, but how could we expand that unit? Moles over liters. So when we're doing a conversion, we should expand it so that we can say, I have 2 liters of, which is times, 9 moles per liter. So I have 2 liters of 9 molar, and that gives me a total of 18 moles. So I have found my moles. Step 1, find my moles. Step 2, we want to find concentration. Concentration is always moles over liters, and we're wanting to find our new concentration. So we need to put our moles over our new volume to get our new concentration, and that's how we do it. Okay, so this is one way of solving a dilution problem. One particular type of dilution problem. We're going to do lots of different ways of solving the problems today. Dilutions 2. So this is a separate sort of a thing. This is where you are given a stock solution. How many people have heard of a stock solution? A few of you. Okay. A stock solution is a more concentrated solution. So this stock is something that you keep in the back room ready to dilute to new concentrations, right? So it's kept on the shelf, ready to dilute. So for example, we have recently run out of 0.1 molar hydrochloric acid that goes in like little bottles that we use in grade 8 and 9 and 10, okay? But in the back room, so what we need 0.1 molar HCl. In the back room, what we have is 1 molar HCl. So this 1 molar HCl is what we would call our stock solution, okay, and we would then want to dilute it down to 0.1 molar. Now, this is a pretty easy one. If you wanted to do this, by what factor are we wanting to change the concentration? We want it to be 1/10, yes? So we need to take our original volume, maybe let's say our original volume was 1 liter. What would my final volume need to be? I would need 10 liters, okay? Now, probably I don't want to make 10 liters of solution. That's an awful lot. I probably only want to make, maybe 1 liter. So I would take 100 milliliters and dilute it up to 1 liter, okay? The math is not always that beautiful, though. So we're going to look at how to do the math around it a little more formally. Once again, though, step 1, what did we find in step 1 before? We found the moles. Guess what we're going to find here? We're going to find the moles. Okay, so step 1 for all of these are all the same. And then the question is going to say, what volume do you need to prepare of the stock solution do you need? So you're going to take those moles and then you're going to calculate the volume. So step 2, you just find whatever you're asked for. Okay? We're going to do this visually to start with. And then we're going to do the math around it. So what we want is we want to make 2 liters of 2 molar, whatever the heck that is, little dots, yes? And remember, what does of mean? Times. And that's going to allow you to find the moles. Okay, so 2 liters of 2 molar, so 2 liters times 2 molar is going to allow you to find the moles. So that's going to be 4 moles. That's how many moles we need to make this 2 liters of 2 molar solution. What are we starting with? We are starting with we're starting with 8 molar solution. That is our stock. How much in liters, how many liters of stock solution do we need? Okay, well, we already know that we need 4 moles, but let's just walk through this in a second anyway. For a second, just visually. We want 2 liters and each of these little doodads here is 1 liter. This one's 1 liter, this one is 1 liter. Each of those 1 liters contains 2 moles. 2 moles per 1 liter, so 2 molar. So if that's how much we want to make, we are going to need to make 4 moles. Yes? Now we're going to look at our 8 molar stock solution. So this is 1 liter of the stock solution. So we got 1 liter, it contains 8 moles. You can see them. What volume of this 8 mole per liter solution contains 4 moles? We have a half a liter contains the 4 moles that we need. Now, how would we do that mathematically? We could say, I need 4 moles. So I've got 4 moles. And I know that I have 8 moles per liter. I want to know what volume I need. Well, could I cancel my moles and find my liters? Would that work? No? Yeah, I need to cancel my moles and find my liters. Yeah? And all I do with this is I take it and I turn it upside down. Yeah? And that gives me 0.5 liters. So you can see how that math works there. Okay? This just shows the math that we just did. Let us try something else here. Okay, so to do a dilution calculation, basically step 1 is always just find the moles. Step 2, you're going to take the moles. If you are asked to find liters, you're going to take liters per mole because that will cancel out the moles and leave you with liters. If you want to find the molarity or the concentration, you're going to take your moles and you will divide it by your new liters. Now let's say that this is too complicated for you. You're like, man, I just want a really simple formula. Well, welcome to M1V1 equals M2V2. What does M stand for? Molarity. That's okay. Molarity. Honestly, I have to be honest with you, I never use this formula because I have a tendency to put the ones with the twos and the twos with the ones, and when I rearrange it wrong because my brain is messy. So if you also have a messy brain, this formula can be a little bit dangerous. But if your brain does not tend to just write down the wrong thing randomly, this is perfectly good. Okay? Perfectly good. Nothing wrong with it whatsoever. Okay, so this is molarity. The other way that we could write this is C1 V1 equals C2 V2. I just mentioned that because it depends on where you go, what university you study at, who your professor is, whatever. They may just choose to use C. What does C stand for? Concentration. Okay, but it's the same dang formula. We have our initial concentrations and volume. We have our final concentration and volume. This formula makes use of the fact that the moles before are the same as the moles after dilution. And how do we find the moles? Well, if we take molarity and we multiply it by liters, that's moles per liter times liter, we get moles, right? Or actually, I should say that's M times V, right? M times V gives us moles. And this is my moles before. And my moles after is also going to be M2 V2 is moles per liter times liters is equal to moles after. And remember, these are the same. And if those are the same, then M1 times V1 is equal to M2 times V2. Does that make sense? Cool. So you can use that formula. Just make sure you put the right numbers in the right places and don't do your algebra wrong. I really like the noon method, but most other people don't. But I'm going to show it to you in case you're one of those weirdos who, like me, likes this method. Your new concentration, N, is equal to the old concentration, O, times the old volume, O, divided by the new volume, N. And that spells N, O, O, N. Noon. The reason I like this is because you remember how we said if you multiply your volume by 4, then your concentration is 1/4. Remember that? If we take our volume times 4, then the concentration is 1/4. Yes? Well, that would be our old volume, 1 liter over 4 liters. Yeah? So this is called the dilution factor. And to me, intuitively, that just makes a lot of sense. Okay? Sometimes people don't like this because they're like, I can't remember. Is it new volume equals old volume and like that kind of thing? It goes in alphabetical order. It goes concentration, concentration, volume, volume. Okay? Concentration, concentration, volume, volume. We're going to try this all the different ways. If 45 milliliters of water is added to 250 milliliters of 0.75 molar K2SO4, what will the molarity of the diluted solution be? So we're going to use the mole method. So we're going to find the moles of K2SO4. And how are we going to do that? We're going to look for the word of. All right, and we're going to say I have 250 milliliters. What should I rewrite that as? 0.250 liters. And what should I rewrite 0.75 molar as? 0.75 moles over liters. So now I have this of, and of means time, so what I've got is I've got 0.250 liters of 0.75 moles per liter, and we get 0.25 times 0.75 equals 0.1875. What will be the molarity of the diluted solution? How do you show that you're solving for molarity? What should you put on the left-hand side of the equal sign? I see so often this. It's not that it's wrong, it just shows kind of an ignorance. Yeah? It's like, you know, if you were writing a formal essay and you started talking in Gen Alpha slang. Yeah? It's just not good. So, how should we show that that's what we're calculating? Yes. Square brackets. Okay. Concentration of K2SO4, and we want this to be the diluted solution, so I'm going to put a little DIL down at the bottom just to say that's my diluted. And that's going to be equal to, I'm going to put my moles on the top, so 0.1875 moles. And what has to go on the bottom? Liters, and that's going to be our new volume. What is our new volume? 0.295 liters, because we have 45 mils plus 250 mils is 295 milliliters, and so that's going to be, whoops, why am I multiplying? I don't want to multiply. 0.295 liters. This is not a titration. Do you remember when I said in titrations never add the volumes? When you're doing a dilution, you add the volumes. Unless they give you the final volume, in which case you don't have to do the adding. Divided by 0.295 equals 0.6355. 6356 to 2 sig figs would be 0.64 molar. Is good? M1V2 equals M2V2. We want the diluted solution and we want its molarity. So M2 is what we don't know. So I'm going to solve this equation for M2. So M2 is equal to M1 times V1 over V2. And now, because I'm kind of stupid, I have to think to myself very carefully, who is M1? Oh, there's only one molarity, so it has to be that one. So that's good. 0.64 0.75 molar. And then I have to think to myself, who is V1? It could be 250, it could be 45, it could be 295. Who is V1? 250, okay? Uh-oh. What did I not do? I did not convert my milliliters to liters, but let's see what our V2 is. What was our V2? 295 milliliters. Oh, what happens to my units? Milliliters cancel with milliliters, so it didn't matter that I didn't change them. I would be multiplying a number, I would be dividing a number on the top by 1,000, I'd be dividing a number on the bottom by 1,000, so I don't need to change them. Okay? So this is going to be, you would end up with the same thing, 0.64 molar. Okay? So that's a very good way of doing it. Used all over the world. Except by me, because I'm weird sometimes. Stuck in my ways is what I am. Noon method. I say, I would like to find my new concentration of K2SO4. I am starting with 0.75 molar K2SO4. So this is my old concentration. And then I'm going to multiply it by my old volume, which was 250 milliliters. Oh, look, once again, I did not change the milliliters to liters. And I'm going to divide by my new volume. And my new volume is 295 milliliters. This makes sense to me because when I look at this, I'm like, oh, look, this is calculating moles, and I'm taking my moles and I'm dividing by my liters. It actually calculates millimoles, and then I divide by milliliters. Okay? And if you look, does that look any different from this calculation up here? Those are the same. And guess what? This one is also the same. You're just doing it in 2 steps. Okay, so none of them are really any different from the other. Okay, 0.64 molar. Technically up here, had you wanted to use milliliters, you could have had millimoles, and then you could have taken millimoles and divided by milliliters, and that would have been fine. So in none of those instances do you actually have to convert milliliters into liters, although usually we do up here because people get confused. They're like, what's a millimole? Oh my God, I hate millimoles. But they're okay. They're just like moles, but smaller. Kind of cute little moles. Okay, here is the procedure for making a diluted solution. So here we have our stock. Concentrated. I don't know why it is in a volumetric flask. I would probably just have it in some sort of storage bottle, but there we are. We would measure out the volume containing the moles we need. So measure out the volume containing the needed number of moles. deliver the needed number of moles into a new volumetric flask. Into a new volumetric flask. There's our needed number of moles. There's our needed number of moles. And then what we do is we add water. To the new volume. Okie dokie? Is good? Okay, excellent. Now, do you remember what you should do when you get close to, on this device, we've got a mark here. That mark should correspond with whatever we want our final volume to be. So if you have a 100 milliliter volumetric flask, you must be making 100 milliliters of solution. If you want to make some funky volume, like 135 milliliters, there's no such thing as a 135 milliliter volumetric flask. You would probably need to make it in a graduated cylinder, or you'd just be like, hey, 200 milliliters sounds good. I'm just going to go with that because there's 200 milliliter volumetric flasks, and I'll just make a little more than I need. What should you do when you find that your water level is getting close to the mark? You should use a dropper, okay? Use a dropper for the last bit, okay? And in fact, you can go one step further. So when you're sort of down here-ish, you can be like, okay, I'm now going to, rather than just pouring it in from a beaker, which is kind of fast, right? You want to do it quickly, so you're going to pour from a beaker, and then you can use a wash bottle. And then finally, we can use a dropper to do that last little bit from here upwards. And then, once you've got it there, is the solution homogeneous at this point? No. So you should put a, what's that? That's a stopper. And you're going to, now, are we going to flip it? We're not going to flip it, because when you say flip, this is flipping. Yes? Anyone want to flip the flask? Like you flip a pancake? No, we're not flipping the flask, we are inverting it. Okay, so invert to mix. No flipping the flask. Is good? Special consideration. Adding water to acid, adding acid to water is exothermic. Most of the time, this doesn't matter, okay? But if you have a strong acid and if it is very concentrated, so when acid is added to a concentrated acid, the heat generated can break the glass, it can cause the water to boil, and splash. But we can alleviate this problem by instead of adding water to acid, we add the acid to the water, which dilutes it. It means you start out with a more diluted solution. Okay? So do as you order, add acid to water. And if you don't know what that means, do as you oughta, which means ought to, which means should. And it works better if you do it in like a New York accent or something like that. Do as you oughta. Add acid to water. Okay? All right. We're going to do this using the mole method. Could you guys please tell me what is the first step of the mole method? Find moles. Do it. What? We missed Mole Day. Yes, we did. I'm very sorry. The 23rd of October, right? 10:23. Yeah, and it's best at 6:02. We should have done something for Mole Day. I didn't even think of it. It was not on my radar. What do we do after we find moles? We find whatever the question is asking us for. And in this case, we are finding volume. Volume is liters. I have moles. I need to cancel the moles and find the liters. So I want the moles on the bottom and the liters on the top. And what am I trying to find the volume of? 2.73 moles per liter. So that's going to be my 2.73 moles per liter. What should I probably do here? bearing in mind that I'm actually doing like a lab procedure with this, and I would need to measure out 0.04945 liters. I should probably convert to milliliters because it just makes more sense. Yes? And in the meantime, I can do sig figs as well, so that's going to become, and I move my decimal place 1, 2, 3 places, which gives us 49.5 milliliters. There we go. Yes? Okay. Now, the other thing you could have done if you wanted to, if you were like this business where you turn it upside down, that's confusing you for me, you could have said what volume, how many liters of 2.73 moles per liter contains 0.135 moles. That would be another way to do it. Yes? So if you like using that of thing, you can definitely do that. Okay? That would be another way to solve it. So many ways. I'm just going to get rid of that because it looks like it's part of the whole calculation. It looks confusing. Do we need to do M1V1 equals M2V2? No? Do we need to do the Noon method? No? Okay. Nah. When is this class over? 1:55. Okay, so we have 20 minutes. Okay. Just be very glad the other block is going to have to watch this video on Tuesday. So super fun. Okay. Mixing two solutions of the same chemical. Now this one, you really do have to use the mole method. Technically that's not quite true, but one of the ways of doing it is to use the mole method. So let's say our chemical is NaCl, for example. Yes? The chemical. So you'll find the moles of NaCl in solution A. You'll find the moles of, for example, the same chemical, NaCl, in solution B. And then you will find the total moles by adding them up. And then you will divide by the total volume. Yes? So if we have 300 milliliters of 0.250 molar NaCl and we add it to 500 milliliters of 0.1 molar NaCl, what is the concentration in the mixture? So one thing you can do is you can say, okay, I have, can we work in millimoles for a second? Can we do millimoles? Yes, we can. We have 300 milliliters of 0.250 moles per liter, which gives us, liters cancel out, 300 times 0.25 equals 75. 75, and we are left with millimoles. Okay, so that's our first one there. Now we're going to do our second one. We have 500 milliliters of, means times, 0.100 mole per liter. The liters cancel out, and we are left with millimoles. So that's going to then be 50 millimoles. So we have 75 millimoles of NaCl, and we have 50 millimoles of NaCl. So our total moles of NaCl is 75 millimoles plus 50 millimoles, which is what, 135? 125. I can't do math. Gosh, what's wrong with me? 125 millimoles. What is our new concentration? (125 millimoles), and then our new volume, we've got 300 milliliters plus 500 milliliters. So that gives us 125 millimoles over 800 milliliters. And the milli cancels with the milli. And we get 0.156. Now, let's think about this for a second in terms of sig figs. I feel like I've done something wrong here. So those have 4 sig figs. So this is 4 sig figs here. And the 75 should actually have 3 sig figs, right? The 75 should actually be 75.0. Yes? And the 50 should actually be 50.0. So I have 75.0 plus 50.0 equals 125.0. Oh. How many sig figs in all my numbers? One, two, three, 4. 1, 2, 3, 4. 1, 2, 3, 4. Oh, so it should be 0.156, and then we have a 2.5, which would then round to 0.1563 molar NaCl. Yes? Which one where? 0.100. Yes, it is. So that 0.100, 3 sig figs here, gives me 3 sig figs here, yes? But then what I do is I take my 50.0 and I add it to my 3 sig figs 75.0. And now I'm doing addition. And I get 125.0. Addition and subtraction can change the number of sig figs. So now I have 4 sig figs. So watch out. Addition and subtraction, they're not nice to you. They make sig figs complicated. Which is one of the reasons why we do this stuff, even though you're maybe like, oh my God, dilutions, I feel like I just know them already. Right? But nuances, details, picky little nonsense. That's how you go from having 93% to having 97%. It's the picky little nonsense. Okay. This just shows it, blah, 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 blah. Do you guys want to try this next one? Now, when you're calculating the new concentration, it wouldn't hurt to label it new. Yes? Did you get 1.84 molar? Yes? Hooray. You do not need to work in millimoles. Totally fine if you don't. I just like exposing you to them because when I learned about them in university, I didn't understand them either. And I was like, what the heck is happening? And it turned out it really wasn't very scary. So the more exposure you have, the better. I think you guys know how to do this. I don't think we need to do this at all, do we? Ion concentration, this is on page 54. If you know that the concentration of sodium carbonate is 0.25 molar, then what is the concentration of sodium? 0.5 molar. And what is the concentration of carbonate? 0.25 molar. There are various ways of showing this work. I guess we should just mention those because at some point you might need to show the work. You can use the particle ratio or the mole ratio to solve this, where you say, okay, I have 0.25 molar Na2CO3, and I have 2 NAs for every 1 Na2CO3. Those cancel out, and I'm left with 0.5 molar. Okay, you could use the mole ratio instead. You could say for every 1 mole of Na2CO3, I have 1 mole of CO3. It's the same thing. Particle ratio and mole ratio are the same thing. Yes? That's one way of showing it. You can write all the concentrations under the dissociation equation. So that's like what I did up here. Yes? I knew this was a 1 to 2 to 1 ratio, and you can just write them underneath. Yes? You do not need to write this ratio. Okay, you would not need to show this line. Whoa, what's happening? Okie dokie. Or you can simply multiply or divide as appropriate. You can say carbonate is the same as Na2CO3 is 0.25, and you can say, I know that sodium is twice the Na2CO3 concentration, and so it is 0.5. Any of those are acceptable. Yes? If I told you the concentration of iron nitrate has 1.20 molar nitrate, what is the concentration of iron nitrate? Do we know that? NO3 is 1.20 molar. Here is the dissociation of iron 3 nitrate right here down at the bottom. What is the concentration of iron 3 nitrate? Yes. 0.4 molar. Or 0.4 molar. Are we good with that? Yes. Okay.
Yeah.
Not much to it. You can show your work many ways. There's some exercises. Feel free to do them if you want to. Feel free to not do them if you don't want to. Yes? Okay. We have 5 minutes left. Is that right? 1:55? Should we just be done? Okay, cool. And then after your quiz, we will get started on solubility math. Okay, but we are churning along and should be done this unit next week, probably. By the end of the week, test the week after. Okay. Yay. Your homework is to do page 41 and to study for your quiz. Page 41 is really short, okay? This is very short. It's just to remind you of what we did yesterday, okay?